reliably operate with wind energy? Well, yes, we can. We have a lot of experience actually doing that in the U.S., and we have a lot of analysis that shows how that can be done. Wind typically does impose an additional operating reserve, which means that of all the flexibility or all the generation that you have online, you may need more of that generation to be flexible than you would in the no-wind case. What do I mean by flexibility? You may need to be able to ramp some units faster when you have wind as compared to when you did not have wind. You may also need to achieve a lower turndown rate, which we saw earlier in a system that has wind, and that's another aspect of flexibility. So the operating reserves represent the additional flexibility that you'll want to have either spinning or possibly non-spinning that could be activated the next maybe 10 or 15 minutes. And what you're seeing in the graph is the red trace that shows the wind generation. I apologize, the legend somehow didn't survive this very well. The actual wind energy in red, and the blue that you see down at the bottom is an estimate of the additional operating reserves that you would want to have on your conventional fleet so you can beat the wind. Well, a couple of interesting things sort of pop out of the graph. If you look at roughly day 155, just to the left of that, you'll see that there wasn't any wind. Well, clearly, if the wind isn't blowing, I don't need to have any operating reserve that I could bring into play if the wind dies down. It's already at zero, and so I don't need additional flexibility for that. On the other hand, if you look at periods of time, there's several of them, day 152, for example, where there's quite a lot of wind, you do need to have additional flexibility in case the wind does die down. It's not going to stop immediately, as we saw, but it can move over tens of minutes of time frame. Moving on to the next graph. What about storage? Do we need backup or storage for wind? Well, not really. I mean, you do need additional operating reserves, and at higher penetration, that operating reserve will probably be higher than it would at lower penetration of wind. But we typically don't back up one generator on the system, whether it's wind or coal or gas. We have other ways of addressing that. So, for example, with contingency reserves, we said, well, it's pretty low probability that a unit's going to trip off, but we need to be prepared for that. And so different regions, different areas have ways of calculating what that contingency is and make sure they have enough reserve that can be called upon in the event that they need it. With respect to wind, you do need some additional flexibility in the system. You don't want to back up the wind with a single dedicated unit because, well, you could do that. It would certainly be reliable, but it's also pretty costly. And of all the integration studies done and even the operational experience in the U.S., we don't really see that happening. You need the flexibility. You don't want to back it up. What about storage? Well, storage is a wonderful thing, and if you have storage, you definitely want to take advantage of it. Storage basically allows you to move energy from one time period to another. Now, that can be attractive in areas where wind tends to blow more at night and not as much during the daytime. So, well, let's put in a bunch of storage, and we can then move that wind energy from nighttime to daytime. Well, that's a great idea. The difficulty with that is that if you don't already have existing pump storage or some other form of storage, it's going to be pretty expensive to add that storage, and the benefit that you get from it is likely not to match the cost. So we think that ongoing analyses of wind and storage really need to look carefully at the economics, and if it makes sense, then you want to do it. One of the recent studies here in Colorado of the Excel system took a look at the impact of pump storage, the existing pump storage, roughly 300 megawatts up at Cabin Creek. There was a simulation that was run by essentially taking out Cabin Creek and saying, let's don't have it at all in the generation mix. What does that do to the integration cost? Well, not a real big surprise. The integration cost without storage went up. You add Cabin Creek back into the generation mix, and the wind integration cost dropped about $1.30 a megawatt hour of wind. So, yeah, storage has value, but it isn't necessary to integrate wind. And if you look at the 23 gigawatts or so of wind that we have running around in the U.S. today, none of those have dedicated storage. some of those, like the one here in Colorado, are on systems that do have some storage, but Excel had that pump storage plant already, and now that plant is being used a little bit differently. As a part of the simulation, the pump storage is operated in we call an economically rational way. When you've got cheap energy and you can pump water up the hill, then you do it. If you have expensive energy and it justifies bringing the water down the hill, then you do that as well. But the pump storage plant did not operate just around the wind plant. It was taking advantage of all the arbitrage opportunities to move cheap energy into more high-value times. And again, you can do that with wind, but you can do it without wind as well. Next slide, please. What about limiting? Are there limits on how much wind can actually be accommodated on the grid? That's a question that I get a lot. In the United States, up to this point, we've studied up to a 25% penetration. And you've seen some of the results from that study, the Minnesota 20% study that actually went up to 25%. At this point, we've not done studies, or at least there are no public studies that have looked at penetrations higher than that. So does that mean we can't go higher? Well, it doesn't mean that we cannot get to higher penetration rates. I suspect that at penetration rates exceeding 25, 30%, we're going to see more challenges. Can we actually do it? Open question. I think we can, but it also depends on the configuration of the non-wind generation fleet. We know that you need more flexibility to operate at higher wind penetration rates. It's probably really more a question of economics. What would it cost to go to a 30% wind penetration as opposed to whether we can actually reliably operate the system? And I'll cover some things a little bit later on that show how we can get additional flexibility out of the grid. Next slide, please. This slide shows a couple of things. On the left, we barely see, I guess, a bar chart that shows a number of wind energy studies and the penetration rates that have been conducted in Europe. Of more interest, I think, here is the graph on the right. This graph came from West Denmark, and if you take a look here, right at around hour roughly 100, a little bit more than that, what you'll see is a period of time when the wind generation actually exceeded the load. Now, this is not a typical event in West Denmark. West Denmark is pretty well interconnected to Europe, and so what happens during periods of time like this, Denmark can export the excess energy to another large market, essentially, and that allows the system to operate pretty well. We do know that large footprints and large markets are a real benefit to helping integrate wind. Next slide, please.